Support for this podcast comes from Invent Together. I bet you didn't know that inventing activity by Black inventors peaked in 1899, and it has never recovered. Black and Hispanic college graduates patented half the rate of white college graduates. That's just one of the reasons why you need to know about Invent Together. When our patent system gets more diverse, our nation will get stronger and more successful. Find out how you can help diverse inventors and unleash economic opportunity at inventtogether.org.
At Capella University, education is as smart as the world around us. With the FlexPath format, you can take classes at your own pace, set your own deadlines, and even leverage your previous experience to move faster. Now that's smart. Learn more at capella.edu.
Hello, Vas here with the How To Academy podcast, the show for and about people who think big. My guest on this episode is Anna Porshaysky, a scientist, engineer, comedian, podcaster, and author of a new book, Handmade, about the art and science of our material world. She joined me to explore her adventures discovering the power and wonder of making things with your hands. Anna, thanks so much for joining us on the show. Your new book, Handmade, is both a memoir of your adventures as a material scientist and a history of some of the most common and important materials in our world. So let's start at the beginning. What is material science and why does it matter?
Well, I always describe material science as being in the middle of the Venn diagram between physics, chemistry and engineering. It's quite a rare subject, actually, as a confluence of different subjects rather than an offshoot of one or the other. So what we do as material scientists is we're just interested in stuff, basically, metals, plastics, ceramics, glasses. And the way that we think about this stuff is that we zoom in to have a look at what atoms are up to inside. So sometimes we use scientific instruments like electron microscopes to do that. Sometimes we just use our imagination to sort of imagine what the atoms are up to inside these materials. And the type of atom that it is, so what element it is off the periodic table, as well as how they bond together and how they can sometimes sort of slip and slide over one another or maneuver around each other. All of that can tell us really interesting stuff about how materials are the way we find them or why they are the way we find them in the real world. So, for example, the atoms in steel can tell us exactly why steel is able to be strong and hard and conduct electricity, whereas a material like rubber is very soft and flexible and doesn't conduct electricity. And so as material scientists, we use atoms to explain all of those materials' properties as we experience them as human beings. So once we understand then how the behaviours of atoms at the tiniest levels can bring about these materials' properties, we can then start manipulating them to bring about the materials' properties that we want. So we can make steel harder or stronger, or make rubber more flexible, whatever it is, we can start them, engineering these materials for our own purposes. Added to that, once we understand what the atoms are doing, then we can select materials for the best materials of the job. And most excitingly, perhaps we can then start inventing entirely new materials that have never before been invented. So very broadly, that's the job of a material scientist.
So you mentioned rubber and steel, but what counts as a material? And the more difficult question, what doesn't count as a material?
That's actually really funny. My friends often kind of troll me with this question, are raisins a material or are clouds a material? And it's actually really foxed me for many years in terms of how we define materials. Generally now, my definition is that it's a material if you can make something out of it. So generally speaking, material scientists study solids and you can make stuff out of solids, but then that can be at all different scales. So you can make bridges out of steel, buildings out of glass and steel, but you can also make nanomaterials that are made up of only a small number of atoms. So the length scales of material science is totally from the nano to the kind of macro. And as well as that, there are liquids that are quite interesting in material science as well. So one really important aspect is how materials form. And quite often materials form from liquids. You melt steel or you melt iron into a mold and it becomes cast iron. that's really important in the tradition of sort of making stuff with materials. So that's a very unsatisfying answer to your question, because it is still quite a woolly definition. But yeah, in general, I would say that it's a material if you can make something out of it.
I'm going to try and make a bridge out of raisins and see if
see how you go. I didn't say it would be a good idea, but as material scientists, it's our job to not choose raisins for bridges.
Becoming a material scientist wasn't a childhood ambition of yours, was it? How did you come across this field?
Yeah, absolutely not. It was a complete accident. As a child, I was always sort of very scholarly, very academic. And I actually loved all subjects at school. You know, the sciences, yes, the maths, yes, but also history and English and music, languages. I kind of just devoured it all. I was a super nerd. And as I was choosing my A-level subjects, again, I chose quite broadly: maths, further maths, physics, music and Spanish for AS level in year 12, and then dropped the Spanish, but kept music. And when I was looking to apply for universities, I actually applied everywhere for physics because I loved maths and I liked the idea that physics was sort of more of an applied mathematical idea. But there was no grand plan beyond that, I have to say. I think I quite liked, if I'm honest with you, I quite liked the idea of also being an agenda minority in a physics department. I liked having that aspect of it as well. Sort of, yeah, being this sort of like badass woman physicist idea. I had this idea in my head. Anyway, so I applied to universities to study physics. And one of the unis that I applied to was Oxford, because I was sort of shooting for the stars, see what we can do there. And I ended up getting an interview for physics, but in the year that I applied, it just so happened that the materials science department at Oxford were really low on applicants for material science because it's a subject that nobody has really often heard of. I certainly hadn't heard of it at the time. But I took them up on their offer because I thought, well, that's just an extra free shot at getting in. And my experience of the interviews was very mixed. When you go to interview, you're there for sort of 3 days. And for the first 3 days, I was doing these physics interviews, but I had the worst cold of my life. It might even have been the flu. I'm not sure. I felt so incredibly unwell. So I would sit opposite these physics professors, you know, asking me questions about physics. And my eyes were sort of streaming. My nose was a constant waterfall of snot. My brain was completely foggy and the whole thing was a disaster. But on my final morning there, I toddled off to my material science interview. And I didn't know what material science was at all, but I remember just having a really lovely chat with 4 professors of materials who knew that I hadn't applied for it. And we just discussed, I remember a hunk of metal that was sort of plonked on the desk between us. It had broken off some component in a car, I think. And we just had a really lovely chat. And a few weeks later, on Christmas Eve, I remember that, the post kind of flopped onto the doormat downstairs and I heard my dad softly climb the stairs and he handed me this cream envelope. And I opened it and it said something like, "Congratulations, you've been offered a place to study material science." And I was like, oh no, what's this? What have I done? But took them up on their offer because, you know, I couldn't turn down an offer to study at Oxford. So off I went to study materials. And actually, it turned out to be just such a fortuitous crossroads and, you know, a turning point in my life to accept that offer, because material science actually was much more suited to me than physics, I think, because it is that bit more applied to the real world. It's much more akin to engineering. So yes, there's a lot of science in it. You know, we do a lot of quantum mechanics in materials and understanding why glass is transparent and why semiconductors conduct electricity. But there was also a huge amount of engineering. So I remember in our labs, we would take apart a lawnmower and look at the different material components and work out what they were and why they were made out of that. So that was how I first discovered materials and then fell in love with it and have never looked back ever since.
And science is just one way of telling the story of the material world, isn't it? Because in your adventures as a material scientist, you've come to realise the importance of a more tactile, more practical, more craft-led approach to material culture. Can you tell us a little bit about how you've discovered the wonder of engaging with material world in that way?
So I would say the background to this is that I have never, ever been artistic or crafty in any way, shape or form as a person. I know I said that I loved kind of all subjects at school, but art and craft was always my Achilles heel, I suppose. And I can trace this back to a very embarrassing and upsetting childhood event when I was in primary school. I remember we had an arts and crafts lesson and our teacher asked us to make cushions, and we were supposed to be, we were allowed to choose whatever shaped cushion we want. And I chose to try and make our new pet rabbit Daisy in cushion form. But unfortunately, it didn't go quite as I had hoped. And this rabbit cushion ended up at this sort of grotesque Frankensteinian shape. It had the nose was far too long. The ears was just like a hump on the top of the head. The tail was too long. And for some reason, I drew this really like manic grin on the front of its face. And I remember showing it to my teacher and kind of seeing her visually, stifle a laughter and try not to burst out laughing at this horrible thing. And I remember showing it to my mum as well, and she had the same reaction. And I was just so upset because A, I'd always done really well at school, and B, I'd really wanted it to go well and it just hadn't gone as I'd hoped. So from that day on, I kind of vowed that I would stay away from artistic creativity and putting myself out there in that way. So maybe unsurprisingly, I followed a scientific route. And then years and years and years later, about 4 years ago, I walked into a place called the Institute of Making, which is sort of a materials science department at University College London. It sits within their engineering department, but it's much more than just materials science. There they have archaeologists and anthropologists and artists and craftspeople and historians and people that look at materials from all of these different angles. And the first day I walked in there, I was sort of confronted by this area in the Institute of Making called the Materials Library. And this is a collection of over 1,000 objects representing the whole spectrum of different materials and different making processes, from, beeswax made by bees to iron cannonballs made by casting iron and everything that you can imagine in between. And I walked in there, and as I was sort of exploring these shelves and picking up these objects, I had this crushing realization that I was a material scientist. Here I was supposed to be the expert in materials. I understood all the graphs and the formulae and, everything on paper I could explain. But I couldn't identify what materials these objects in front of me were even made out of, let alone at the start of our conversation, I said that material science is studying how atoms give rise to materials properties. Well, I was used to materials properties like hardness and flexibility and all that sort of thing. But suddenly before me, I was confronted by materials properties like intrigue and disgust and menace and all of these properties of these objects that couldn't be explained by atoms. And so that was a sort of terrible realization that actually here I was thinking I was the expert, but I really wasn't. And the gap in my knowledge was this idea of making and craft and hand making objects and how to transform a material like porcelain that's just a normal ceramic into a teacup that has sophistication and these intangible properties that can't be explained by science. So that was the realization. And so that set me on this quest to find out from craftspeople how they do this, how they transform materials from just collections of atoms to objects that we know and love in our everyday lives.
Let's talk about some of your adventures in making and what you discovered about some of our favourite materials. Glass is, I suppose, the material that we most associate with science, I guess through the symbolism of the test tube or the beaker. Can you tell us, why is glass so integral to science? Why don't scientists use metals to make their equipment?
So, yeah, glass has always been this material in science that has it's been the fitting sidekick, I suppose, to scientists throughout the centuries, really. The alchemists of old used glass to contain their experiments as they were trying to transmute lead into gold because it's transparent. So you can put materials into glass and you can see them change colour and bubble and boil and react together from the safety of outside. You can observe through glass. It's also it's got a very high melting temperature, so you can put your Bunsen burner onto glass happily and hopefully it's not going to melt. And it's very unreactive as well. So if you've got your experiment sitting in glass, the chances are that glass is just going to be a passive bystander. It's not going to start reacting and messing up your experiment. So that's it sort of in the lab. But then when you start thinking about it, as I did in the book, the glass is everywhere in science. You know, we peer down it when we look down microscopes. We peer through an eyepiece and lenses that magnify the very, very small. And we also look down lenses in telescopes as well, made from glass. And so it magnifies the very, very big for us to see as well. So it's always been this constant companion to scientists throughout the ages. But it wasn't until I really started getting my hands onto glass that I properly understood how it behaves underhand. So in my research for the book, and as I write about, I go and meet makers and glass blowers who actually manipulate this stuff to make scientific glassware. It came as a real surprise to me that this stuff isn't just made by a machine. Actually, there are artisans who make the beakers and petri dishes and funnels that we use in the lab. And to see them lovingly create this stuff out of gooey, molten glass, it changed the material for me from being something that is just looked through to something that can be really looked at and celebrated and experienced in a very hands-on way.
So someone told me a few weeks ago that glass was actually just a very, 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 very slow-moving liquid, because in churches, the stained glass windows often bulge at the bottom. And is that just a myth?
That is unfortunately a myth, yeah. But there is a very interesting atomic reasoning as to why we might say that glass is, some people describe it as a supercooled liquid. And the molecular reasoning is this. In liquids, molecules are randomly oriented. You know, they don't have any strong bonds between them, so they can kind of swim around and move over one another and fill up any container that they're in. And they just sort of, slosh about quite freely. Some materials, and I'm going to now stop talking about glass and start talking about ice, and we'll come back to glass in a minute. Some materials like ice, they are what we call a crystalline material. So in crystalline materials, the molecules and atoms, when they solidify, the atoms become sort of bound up in a very neat crystalline structure, a very neat series of rows and columns in 3 dimensions, where all of the molecules will happily sit. But it's very regimented, it's very predictable. And the way that water molecules are arranged in ice, the angles between those we can see in the real world. It's why snowflakes have 6-sided symmetry, because the angles between the water molecules as they line up in that regimented structure follow those of a hexagon. So thinking about those crystal structures then, because all of the atoms are very neatly lined up in these regimented rows and columns, when you heat ice from below 0 to 0 degrees, once we hit 0 degrees Celsius, suddenly that temperature is enough to suddenly break all of the atomic bonds in between those atoms. So the material goes from being ice as a solid to water as a liquid, and then those molecules can flow around and be liquidy. Glass is different. So glass is not a crystalline material. In solid glass, the molecules don't have any kind of order to them. They are bonded together with strong bonds, but there's none of these regimented rows and columns like there are in ice. Instead, it's what we call an amorphous structure. So they're just sort of in this randomly organized kind of tangled configuration in a 3D network. So down a microscope, if you were to look at the atoms of, let's say, water as a liquid and glass as a solid, those atomic arrangements look very, very similar. So when you look down a microscope at glass, it does look like a liquid at the atomic level. The difference is that those bonds are there's very, very strong bonds in glass. So that's why we might think of glass as a liquid. However, it's not. At room temperature, it is a solid. But the reason that we would describe it as a supercooled liquid is this atomic arrangement. Now, when you heat glass up, you don't get the kind of melting temperature like you get with ice at exactly 0 degrees Celsius. What you get is a gradual breaking of those strong bonds over a range of a couple of 100 degrees Celsius, so that to a glass blower, when they're heating their glass, what they'll experience is a gradual softening of the material, which can take, seconds or even minutes to come about as they're heating the material. And this softening is called the glass transition. And so that's the transition where the material goes from being more like a rigid solid to more like a runny liquid. But there is no sort of one defined moment where it's solid and then it's suddenly liquid. Now, going back to these medieval churches, When we observe medieval churches today, obviously they've been around for hundreds of years, and the glass is slightly thicker at the bottom. Now, you might think that that is because the glass, as a material with a liquidy-like atomic structure, that has flowed downhill over the centuries. However, we now know that that's not the case. We now know that this is like that because medieval church glass was made with a process called the crown glass process. And here, what the medieval glaziers did was they created a softened lump of runny glass. Notice that I didn't say molten because it hasn't melted because it's not crystalline. So you've got this runny glass, and what they did was they spun it in a sort of circular motion. They would spin this glass, so centrifugally it would kind of splay out into a sort of wide, flat sheet. And they would then cut out their little, quite often sort of diamond shapes, cut out those diamond shapes of glass and then lattice those together with lead. Now, because of this centrifugal spinning, one side of the sheet is going to be thicker than the other. And so it makes sense then, if you've cut out your rectangle of glass and one side is slightly thicker than the other, it would make sense for you to put the thicker side at the bottom rather than at the top, so that your window isn't top heavy and isn't going to, it is less likely to kind of fall on the congregation and cause some kind of terrible accident. So that's a very long-winded explanation, the atomic explanation as to why medieval glass is thicker at the bottom than it is at the top.
Excellent. Why are our phones made of glass? Because it breaks really easily, even to this day.
This is now entering the intangible realm of human whimsy and our desires not being compatible with traditional choices in material science that we would make. So glass as a material, as we know, is very brittle, and it's very what we would call low in toughness, which means that it's very easy to shatter and break. We experience this, unfortunately, in the pub sometimes when we break a pint glass, or if you sit on your glasses, all the time, glass lets us down because it's so brittle and fragile. And phone screens are no different. But glass also is quite heavy. It feels quite nice. It looks very nice and glossy. And the alternative material to glass in a phone screen would probably be something like transparent plastic, something like Perspex maybe, again, quite hard and very see-through, so brilliant for a phone screen. The reason I think that we don't use plastics in phones is that we as users just don't want it to be made of plastic. When you touch glass, it feels cold to the touch. It's also very, very hard, so it doesn't scratch as easily. If our phone screens were made of plastic, they would feel warm and they would start getting scratched and scuffed up a bit. And so glass in our phones, it's quite a luxurious material in this setting. And so with our phones, it makes us feel like we're holding an item of luxury in our hand. And it makes us feel like we're someone that deserves items of luxury. And I would be really interested to talk to phone designers and developers about their materials choices and, see if they've done studies on people to assess their feelings of these different materials, because in many, many ways, plastic would work better in terms of not smashing on a phone screen. But for some reason, they just keep holding on to this material of glass. And the reason is human whimsy.
I like to think Steve Jobs knew that the idea of a warm iPhone would be disgusting right from the beginning.
Yeah, so true.
There would never be enough girls. There'd never be enough money. Somebody would always have more.
We're not out of business. You're going to take over our payroll. And he said, no. My heart just sunk.
I was completely and totally wiped out by it.
You just heard some of the raw personal stories you find on Secret Leaders, the UK's startup podcast, where I get founders of companies like Monzo, Joe Malone and Brewdog to reveal all. If you're fascinated by how real visionaries think, if you want to build a business one day, if you want to be more successful, then check out the Secret Leaders podcast.
Are you good with people? Maybe you're organized or have a knack for numbers. Well, then chances are you've got skills that could lead to a new career. A Google Career Certificate can help you get a foot in the door with top employers in fast-growing fields like IT support, project management, data analytics, and user experience design. It's professional-level training developed and taught by Google employees. And it's all online, so you can learn around your schedule. Put your skills to work. Go to grow.google/certificates.
So you have a familial connection to one material in particular, through your grandfather George, who lived through most of the 20th century. and was very involved with a very 20th century material, plastic. Can you tell us his story?
Oh my gosh, this is the story that has been sort of passed down through family. When I was little, my granddad George was in his sort of 80s and 90s, and he was always this very sort of big figure in our family and in my mind. He was born in 1910. So when I knew him, he was an old man, and whenever we went to visit him and I sort of heard him speak about his life, he hinted at this life of kind of grand and terrifying adventure. But as a child, I was always a little bit shy and didn't really want to ask more. And I found out at his funeral a few years ago that his whole life story had been written down as a memoir. And a few years later, I sort of got round to reading this memoir. And as I was reading it, by this time I was a material scientist, and I came to notice that this material of plastic was constantly intersecting with his life experience, and at times even his life was saved by this material. So it made sense for me when I was wanting to tell material stories to tell the story of Grandad George, and that story is this. He was born in 1910, which was actually just a few months after the first ever synthetic plastic called Bakelite was invented. So George and plastics were pretty much born at the same time. And he was born in Russia, and by the time he was a child, the First World War had started and the Russian Revolution was well underway. And him and his family had to flee Moscow, where they were living, to the east to escape the war. And so from the age of about 5 or 6, he was a refugee. And there's an incredible story here where he was travelling on the Trans-Siberian Railway with his mother and baby sibling, and he got off this train to go and fetch some hot water. It was a steam train, of course, because this was the 1910s. And this steam train, whenever it stopped at a station, you could go to the front and you could collect hot water off the engine. So off he got off the train, but there was no hot water by the engine, and there was a huge queue of people waiting. So he decided to go round to the station buffet to get hot water instead. There was no hot water there either. But someone there said, oh, there's a restaurant just over the town square, see if they'll go and give you some. So off he toddled. He was 7 years old at the time. Off he toddled to go and get this water, and the cook in this restaurant obliged him and gave him this water. And as he was making his way back to the train, he heard an engine whistling. And when he got back to the platform, he noticed that the train that he was on with his family on it was no longer there anymore. So he was alone in the middle of Russia during the middle of the Russian Revolution, age 7, with just this kettle of water. And he just sort of sat down by some railings and started to cry and eventually fell asleep. And a Polish family took him in that town, cared for him for a while, and he eventually joined the easterly migration of refugees with that family. And the next part is completely mind-blowing to us living now, but he just found his family again in China.
In China?
Like a year later, he just happened to run into them because his dad had actually set up a station to reunite lost children with their family, because his wasn't a unique story. And so he walked into this office one day trying to find his family, and it turned out that his family were the ones running this sort of reuniting service. So they lived in China for a while and then moved on to Tokyo with his dad's job. And as an aside, my dad always told me he sort of learned bits of Chinese and Japanese when he was there. And my dad was always so embarrassed whenever, years later, they would be in London at the Science Museum and Grandad George would overhear a Japanese family and go over and talk to them in Japanese. And my dad would be like, oh, God, Dad, you're so embarrassing. So anyway, so he ended up in Japan. They went back to Poland eventually, sort of after the war was all settled down, and he spent his teenage years and his university years in Poland, in Warsaw. He studied aeronautical engineering. And then the Second World War broke out, and he again had to flee because Warsaw was not a very good place to be during the Second World War. So his trip then took him down south through Hungary and Budapest, and then he ended up in Athens in Greece, got a boat over to Marseille, worked in Paris for a bit as an aeronautical designer. Then Paris got invaded by the Nazis, so he fled on a motorbike. I'm paraphrasing the story now. Fled on a motorbike south, was trying to get to Gibraltar, but there was a military zone declared around Gibraltar.
This is a blockbuster movie.
I know. they couldn't get into Gibraltar, so they got on a boat to the North African coast, convinced a taxi to drive them to Casablanca, found a boat and just got on a boat. And they didn't know where this boat was going, but they couldn't stay where they were, him and his friend. So they got on this boat, and it turned out that this boat was going across the Atlantic Ocean. So he had a transatlantic voyage for a couple of weeks. And by this stage, he had absolutely no possessions on him at all. All he held was a couple of, bits of paperwork, a packet of cigarettes, the clothes that he'd been wearing for the last fortnight, and an inflatable rubber Lilo mattress. Now, this was a sort of luxury on board, and he would hire this mattress out during the day in exchange for food and small amounts of money. And this rubber mattress is, of course, made of plastic, made of natural rubber. And it's really interesting to me that this item was made of natural rubber at the time, because the Second World War was a time where synthetic plastic research exploded, because not only was rubber a really useful material for the military, but it came from rubber trees, in tropical climates, which during wartime is not a very accessible place to trade with or to get materials from. So Europe and America at the time developed a whole load of synthetic plastics around the Second World War in answer to this disruption of supplies. So anyway, George's mattress was made from natural rubber, and he eventually made it with the mattress over to Nova Scotia in Canada. That's where the boat was going. Some of the refugees got off there and became Canadian. He stayed on the boat, travelled back across the Atlantic again, and landed in Cardiff Docks in September 1945. And then that was him then, as a Brit. He stayed in the UK ever since 1945, moved to London as an aeronautical designer. But after the war, there wasn't much work for aircraft designers anymore. So he decided to start a company with his Polish mate that was making plastics and plastic goods. At the time, these materials were up and coming. As I say, new synthetic plastics were being made during the Second World War. And so afterwards, there was this huge explosion of plastics that were accessible household objects. So they were making things like combs and soap dishes and buckets, things like that would previously have been made of metal or wood. And so that relatively strange new material in this relatively strange new country for him of England and London was really what enabled him to find his feet as a sort of migrant in this new country. And he settled in London. The business boomed. They moved it to Croydon, and the company actually still exists, although they didn't manage it for very long. And so for the rest of his life, for the second half of the 20th century, George observed plastics go from these, new and exciting materials that had lots of very lucrative commercial applications to just being everyday materials that were so common and cheap that they became disposable. And, we saw packaging and clothes even, and this mass production suddenly exploded with plastics because they were so cheap and available. So by the time George passed away in the early 2000s, his whole material world really had transformed into plastics. His clothes, carpets, windows, personal objects, cups, everything, TVs, everything had transformed into plastics. And so that really is his story from being born at the same time as plastics to seeing this rise of this massive material family. And then, of course, in recent decades, the fall of that material family as well, as we came to realise that perhaps it wasn't such a good idea to be mass producing so many objects that were destined for a very short lifetime in our possession, but destined for a very long lifetime in landfill and in the environment. So that chapter really is the story of the rise and fall of plastics, and an assessment really on where we are today with plastics and where we might need to go in the future.
Now, the environmental effects of plastics are complex, aren't they? It's not the simplistic picture we might have in our heads, because in some ways, plastics mitigate against greenhouse gas emissions. Can you speak a little about that?
Yeah, so because plastics are so incredibly lightweight and very, very cheap and easy to mould, they are brilliant materials for kitting out portable things like aeroplanes and cars. And the weight savings that we gained from plastics, most of our aircraft now are made of carbon fibre reinforced plastic components. And, the wings and the chassis, a lot of them are made of plastics now. And the weight saving that we get from that compared to materials like aluminium or steel saves on aircraft fuel and vehicle fuel. And so it's this question of plastics good or bad is it's so complex. And yeah, in many ways, plastics have saved the environment in terms of greenhouse gas emissions, even though they're derived from fossil fuels, because of these weight savings. And in food packaging, they stop a whole load of methane from getting out into the atmosphere by extending the shelf life of goods and stopping, perishable foods from going rotten and releasing methane. So it's some people's whole careers and jobs to really assess the actual sustainability benefits of plastics. And this research is still ongoing today. And it's such a complex problem. And there are so many different factors and stakeholders in this question that I don't believe that it is just a question of replacing plastics with other materials. It's much more complex than that.
Now, plastic is a material with a somewhat bland personality. And as you've alluded to, one of the questions that you're trying to answer in your book is whether materials have personalities that are inherent to them in the physicality of the material, or that come from the process of making the object. And one material that has a very distinctive personality, a very macho personality, is steel. Now, your first adventure with steel did not displace this belief. How did you come to be in Utah trying to break a land speed record? You alluded earlier to wanting to be a badass woman physicist.
Exactly. So here was me living out my lifelong dream as a badass engineer in the salt flats of America. So this was an opportunity that I got actually through an alumnus from my college in Oxford. This person had studied material science and then decided to go on to a career in finance, earned loads of money and spent all that money on a supercar. And every year he would go to the Bonneville salt flats to try and break a land speed record. Now, in his sort of philanthropic mood, he decided to take a student from the uni with him to go and try and break this land speed record. So there I was, aged 20, with long blonde hair, vegetarian, studying for a degree at Oxford in material science. And then everyone else on this team was a middle-aged Glaswegian car mechanic. So immediately it was a very odd team dynamic. And right from the off, I wasn't really sure what I could offer because, like I said at the beginning of our conversation, I know the theories and the formulae of materials, how they work on paper, but I don't know. I can't use a spanner. I don't know how engines work. I know how the materials in them work, but I've got no idea what the practical use of this stuff is. So immediately from the beginning of that week, I was feeling a bit imposter syndrome-y. And as the week went on, my fears were not at all alleviated. They were very much confirmed that I was really no use on this team at all. And pieces on this car kept breaking because it was engineered bespoke. So this supercar was trying to get up to 313 miles an hour on a 1 litre, I think it was a Kawasaki motorbike engine, which don't traditionally go up to 313 miles an hour. So we're really pushing these engineering components way beyond their limits. And on about day 3 or 4, we'd broken most of the components on the car, and we had a pass at this land speed record. I think we got up to about 200 miles an hour, and then something in the engine went bang, which is bad, turns out. And we got the car back to our kind of pit stops on this salt flat and opened up the engine, and out fell this sort of glittering waterfall of black engine oil. And the glitter in that waterfall had 10 minutes ago been the steel components of the gearbox inside this car. So basically we'd completely shredded all of the cogs inside the gearbox. And out of this puddle of black engine oil, I picked out 2 little oblong teeth, which had previously been the ridges on the sides of the gear cogs that were mediating the force of the wheels of the car. And I noticed something very, very strange about these. As I sort of smeared off the engine oil, I saw that one of them had broken off with what we call ductile fracture. And this is the same way that you would kind of break a Snickers bar. If you were going to snap that in 2, it would sort of bend and it would flow and it would pull apart quite slowly. And you'd end up with like a rough fracture surface. That's what the first one looked like. And I knew that this was ductile fracture. The second one was completely different. The second fracture surface was flat and shiny, like a mirror. And this was brittle fracture. I knew from my lectures in Oxford, I knew that this was brittle fracture.
It's good to know that you learned something useful in Oxford.
Right, exactly. So brittle fracture is it's like what you would if you were going to snap a piece of dark chocolate, right, it would snap really quickly and you'd end up with a very flat fracture surface. That's brittle fracture. But this was mad, right? Because these two components of steel were exactly the same material, exactly the same component probably of the gearbox, but they'd broken off in extremely different ways, one like a Snickers bar and one like dark chocolate. So the question was, what the hell was going on? And I remembered from my lectures that there are some factors that might dictate whether a material like steel breaks with brittle fracture or ductile fracture. One of those is temperature. So if you were to put a Snickers bar in the freezer and then attempted to, break it, it would be far more likely to snap like dark chocolate than to sort of pull apart. It would certainly be much more difficult to do that. But this couldn't really have been the case here because, the gearbox was probably the same temperature. Some of it wasn't going to be freezing cold to cause that brittle fracture. So instead, actually, what I thought was that it was probably the speed at which these two components broke off, because if you break steel, or actually Snickers, very quickly, what happens is the material doesn't have time to do all this lovely bending and flowing and sort of creating this beautiful ductile fracture surface. It doesn't have time to do any of that. It just snaps clean off like a piece of dark chocolate, like brittle fracture. So I think probably what happened was the ductile tooth came off first and kind of bounced around in the gearbox, smashed into the second one, came off really quickly with brittle fracture. So I was sort of thinking about this as I stood on the salt flats with these like oily pieces of steel in my hand. And I considered telling the team about my ideas, but my confidence actually failed me because I didn't see what use my expertise was going to have at this time, because obviously the gearbox was broken. And I did feel this sort of impenetrable macho culture around steel. We think of steel, not just material scientists, everybody thinks of steel as being quite a hardcore engineering thing, right? We build bridges and railways and buildings and engines out of this stuff. It does have this macho personality.
There's a reason Superman isn't the man of wool.
Exactly. That would be like the feminist spin-off in 2040 or something.
I'd prefer that, to be honest.
You heard it first. Let's make it happen. So it does have this massively macho personality. And when I was coming to write the book, I wanted to see if this could be subverted in some way. So I met a blacksmith up in Glasgow called Agnes Jones. And she is an artist blacksmith. So she doesn't, make sort of engineering things with steel. She makes art out of steel. And her artwork, she describes it as line drawing, but with steel. So she puts her steel bars in a forge, heats them up to over 1,000 degrees, and uses hammers and welding equipment to bend this steel into kind of beautiful, intricately shaped, curved drawings, but as sculptures. And a lot of her work it's like life drawings of female forms. And so there's lots of kind of sweeping shapes. It's extremely beautiful, and it's very feminine, I would say. And completely, in my mind, subverted this macho personality that I had always associated with steel. And when I had a go at blacksmithing with Agnes in her workshop, I always thought of myself as being quite a strong person. I'm a strong swimmer. I've got reasonable upper body strength. But when I tried hitting steel with a hammer, I found out that I was not very strong at all. And in fact, Agnes, she's a very slight woman, but she was able to bring so much heft and force to this craft, all through technique. And so that really highlighted to me, steel doesn't need a lot of force and strength. It just needs sort of technique and care and craft. So for me, this discovery really, like I say, subverted my whole idea of what steel could be, and steel as its material personality and where it sits in our culture.
So in the pandemic, a lot of us have taken up tactile hobbies like baking. But for you, the therapeutic tactile art is making stuff out of clay. Can you tell us a bit about your experiences with clay and how you came to realise its power for you as a therapeutic tool?
So I first discovered clay during my PhD, not in the lab, but in a totally different setting. My experience of doing a PhD was very difficult. I was in a lab with a bully, basically. There was a guy there who it kind of made my life very, very difficult. And throughout that time, I became really quite depressed and lonely because my working life was being made so difficult by this person in the lab. And so looking back now, I kind of remember that whole duration, that whole time, as kind of a sea of depressive grey. And one day in the lab, the only other woman that was in this research group, she asked me if I wanted to go over to the Institute of Making to try and throw pots on the potter's wheel. And I said, sure, that sounds like fun. Anything is better than being in this lab. And so off we went to the Institute of Making, and we tried pottery. And I remember those afternoons of pottery with her as sort of in just brilliant, happy Technicolor against this general sea of depressive grey. And we would sit side by side at these potter's wheels with this clay, slamming it down on this spinning wheel, trying to form some kind of circular pot or vase or cup, mostly very, very unsuccessfully. Pottery is extremely difficult, but that didn't actually matter, because it was the process of working with this stuff and the liberation of being quite bad at something. It's quite funny when it goes wrong, and there's no pressure with clay, unlike something like steel where you're heating it up and hitting it and reshaping it. With clay, you can constantly reshape it, and if it goes wrong, you can actually just cut it off the wheel, put it into a recycling bucket, and then it can be recycled for the next user. So it's a zero stakes game with clay. And we would sit side by side together on these afternoons, and in each other we kind of found a fellow silent sufferer in that difficult environment, and were able to sort of share and offer support to each other while we were shaping clay. So for me, clay has always represented a kind of escapism through making. And after finishing my PhD, I didn't touch clay for a few years until writing this book. And then I revisited this with brilliant potter Darren Ellis, who actually taught me how to use the wheel. And
was that what was going wrong in the first place?
We were very much self-taught at the beginning, yeah. Which turns out is not a very good way to learn how to do pottery. So Darren sat down with me on the wheel and really showed me, the basics of how to do it. And through that, I gained, I suppose, acceptance of everything that had happened. And towards the end of my PhD, I remember we, this is slightly morbid, but we decided to make small vases in our pottery afternoons. And into that vase, I have put a burned copy, the ashes of a burned copy of my PhD thesis, as a kind of symbolic screw you to the establishment and everything that happened. And maybe listeners are going to think that I'm gone slightly off the rails when I describe that. But for me, it was very much a sort of a healing process of creating this pottery object, putting the ashes in there and moving on.
What's your favourite material?
Oh, it's such a tough question. People often ask me this, and it changes all the time. And actually, it depends what the purpose is for, I think. As I say, in this book, I tried making with 10 different materials, and the craft that I've taken forward since then is knitting. So I would say today my favourite material is wool. It's one that it's unfamiliar as a material scientist. We don't study really any kind of natural materials like wood, stone, wool. None of these things we actually study, which is mad because those three materials I just mentioned, wool, wood and stone, are very important for society and history and the way that...
What's going on there? Why are they absent from the curriculum?
I think it's because, firstly, they're extremely complex materials. Let's take the example of wool. Wool is created by the biological process of evolution through, iterative animal processes and biological processes. Wool has been honed over millennia to be just an incredible fibre. And actually, as material scientists, we've still never made something as good as wool. The combination of properties that wool has is completely unique, and it's all down to the incredibly intricate way that wool is made up of atoms. I said right at the beginning that as material scientists, we like to look at how atoms click together to build materials. Well, in wool, there is an insanely complicated hierarchy of structures. So you start off with this sort of long molecular chain, so just atoms in a chain in an amino acid. That molecular chain is sort of twisted And then 3 of those are twisted around each other to make a sort of rope called a fibril, I think. And then more of those are twisted around each other. And then more of those are twisted around each other. And there's this just massive complex hierarchy of structures within wool. And those structures give wool its flexibility, its strength. There are fatty acids in there which make it, actually fats I should say, that make it sort of waterproof and resistant and fire resistant. And we have never, and it's thermally insulating, we have never as material scientists been able to come even close to creating this material of wool. And I think the reason that material scientists don't tend to study stuff like this is that it is just so complicated. Wood is the same, wood is made from, it's basically a composite material. So you've got lignin and you've got cellulose and hemicellulose. And this composite material is so intricately developed and evolved and sort of positioned together that it's intimidating as material scientists to look at what biology has done and these incredible materials that it's created and attempt to replicate them ourselves. And this is an area of material science that is really hot at the moment called biomimicry. And it's this idea of looking to nature and getting inspiration, seeing why can a gecko stick to the ceiling? How can mussels clamp themselves onto rocks with waterproof glue? Can we mimic some of that stuff in the lab? But it's an area of ongoing research, and we're only really just scratching the surface in terms of being able to mimic this majesty of biology.
And I know your infectious enthusiasm will have inspired our listeners to engage more with the material world. It certainly inspired me. Where can our listeners start if they want to become more involved in material culture?
Well, read my book, please. It's called Handmade, A Scientist's Search for Meaning Through Making. That, I really hope, will give readers a sense of identifying how materials intersect with our lives, I think, and noticing material cultures and noticing materials choices and why we make certain objects out of the materials that we do. Noticing those personalities and how we can subvert those personalities. Noticing the incredible properties that we so often take for granted, like how a mug is able to protect your hands from scalding hot water with just a couple of millimeters of material. If you were to make a mug out of metal or plastic, you'd probably burn yourself, but ceramics, amazing. Noticing those materials' properties and the choices that craftspeople have made throughout the centuries to make our lives, better and more vibrant and exciting. So I recommend starting with the book, and hopefully that will then sort of get people's imaginations fired up in terms of, how materials can intersect with our lives.
Anna Pulshaysky, thank you so much for joining us on the podcast.
Thank you for having me.
This week's show starred Anna Pulshaysky. It was produced and presented by me, Vas Christodoulou, and edited by John Doughty. Anna has her own podcast, which, like her new book, is called Handmade, and available wherever good podcasts are found. And, of course, you can find more scientists in our own podcast archive, from physicists Brian Greene and Neil deGrasse Tyson to psychologist Simon Baron-Cohen, anthropologist Rebecca Ragg-Sykes, and neuroscientist Gina Rippon. Until next week, stay safe, and thanks for listening.
There would never be enough girls. There'd never be enough money. Somebody would always have more.
We're not out of business. You're going to take over our payroll. And he said, no. My heart just sunk.
I was completely and totally wiped out by it.
You just heard some of the raw personal stories you find on Secret Leaders, the UK's startup podcast, where I get founders of companies like Monzo, Joe Malone and Brewdog to reveal all. If you're fascinated by how real visionaries think, if you want to build a business one day, if you want to be more successful, then check out the Secret Leaders podcast.
Okay, parachutes ready.
Boy, the things I go through to get auto loan rates as low as 0.99% APR for 60 months on new vehicles with PenFed.
You are aware that you don't have to be a military member to save hundreds on your auto loan, aren't you? Anyone can join PenFed.
As someone terrified of heights, I probably should have looked into that.
Probably.
Drop me off at the shore.
PenFed Credit Union. Visit PenFed.org/autos or call 1-800-247-5626. Advertised rates available through the PenFed car buying service. To receive any advertised product, you must become a member of PenFed, insured by NCUA.